Hey, let's get into the homework solutions. This first one was part of a massive pre-lecture note on the history, which was out of the textbook, and then we also made a little summary of that for y'all. So anyway, I was going to point to the lecture notes to point out that you had all this info, but let me just do it this way. Recall that here, loss is a function of wavelength. With something like this, there's a window around 1310, there's this OH spike due to the water vapor, and then there's a lower loss window around 1550 nanometers. And then this was 1310. And so actually first generation was way over here at 800 nanometers. I'm not even going to draw that, but that's where they started, and they said, well, loss is a lot less over here, so let's go there. But they said, hey, loss is even smaller at 1550 nanometers, so they really wanted to work over here, but the dispersion was so bad, right? So dispersion curve, the conventional fiber had its zero dispersion wavelength at 1310 nanometers. So they would have moved directly over to 1550 nanometers where loss was less, but the dispersion would have been terrible. So they said, nope, we'll go with 1310. But because the loss was less over here, they wanted to go to 1550, and so they ended up creating this dispersion shifted fiber that has a zero dispersion wavelength at 1550 nanometers. Okay, so that's part of the history, and you have the full summary of the whole history, right? So getting back to answering the homework, loss was less at 1310 nanometers in conventional fiber. Like I said, that already is no. It wasn't less at 1310. That wasn't the reason to start at 1310. It was zero. It was dispersion. So this is already false. So this is the one that I gave you 10 free points on because I hadn't covered that. But now that I covered it, I brought it back in. And any questions on that one? Okay. In a EDFA, erbium doped fiber amplifier, the pump wavelength has to be what? Bigger than or smaller than? Yeah, I kind of flip things sometimes, so I'll go slower. And whereas I can remember a picture, right? 10, 20 years from now, you can remember a picture, right? If you need to get in a debate about this. But it has to pump the atom up to some excited state. And I can't use the same color for the pump as I can with the signal, or I'd get confused. I'd be looking at my pump thinking it's signal, right? So they have to be different colors, right? But the objective of the pump is to create the population inversion. So I pump it up to some level, and then it trickles down here, and then it hangs here for a longer lifetime. Eventually it will decay. All things will go back to their lowest energy state, but it's a matter of time constants. These little spin flip transitions are really fast, whereas this is more of an atomic orbital jump, and so it's slower. It's like milliseconds or something, which is very slow for optical signaling. Right? So now I have a population inversion that corresponds to this jump is Planck's constant times the frequency. So then this is stimulated emission of radiation the same way a laser works, except it's just the amplifier part. If I put mirrors around an amplifier, I've turned it into a laser. And then it has all those resonances like I drew last time. But getting back to trying to solve the question, this is going to be a bigger jump for the pump. Right, so the frequency that I pump it with has got to be bigger than this one that I'm using to create an amplifier. So a photon comes in and it stimulates this jump, and so that releases a photon of this color. And here's the one that came in to stimulate it. One came in, two came out. That's an amplifier. Right? So it's amplifying this red color, but I'm pumping it with this other color, right? That has a higher frequency. It's bigger than the frequency of my signal, which corresponds to the 1550 nanometers. So someone could ask this in a different way. They could say the pump frequency has to be bigger than or smaller than the signal frequency. Then pump frequency has to be bigger, but because frequency times wavelength is some constant, Einstein's speed limit divided by the index of refraction, the phase velocity, then if frequency is bigger, that corresponds to wavelengths that are smaller. Right? With me? Questions on that? Okay, like I said, multiplying and dividing. Now, if you don't like this, that one goes up. This is a constant, therefore that one has to go down approach. Use numbers if you prefer numbers. Right? You can set numbers equal to 1. Pretend like all these other numbers are 1, and then pick a simple number to see whether it goes up or down, like I showed examples of. So this wavelength has to be longer, bigger. No, frequency is bigger. See, check yourself on a test, all right? Don't let flipping things upside down get the wrong score. You'll have plenty of time. You'll have 5 times more time than you need on the exam. But frequency is bigger, so the wavelength is smaller. So smaller is a key word here, all right? And so another way of saying smaller is it's a shorter wavelength. Questions on that? Okay, and in practice, you don't need to memorize numbers here, but for signal wavelength at 1550 nanometers, EDFA pump wavelength is typically 1480 nanometers, or another popular one is 980 nanometers. Okay, so if I'm pumping with 1480, I go up to some set of energy levels. If I'm pumping with 980, I go up to some other set of energy levels. And both are used in practice. Questions, comments? All right. In advanced modulation schemes that use PSK or QAM, the detector is sensitive to phase. True or false? True, right? This one has the word phase right in it. Phase shift key. Right. I said that could be different phase shifts instead of different amplitude. Instead of 4 amplitude levels, I could have 4 phase shifts. I could have 8 different phase shifts, 8 circles on a dot, or 8 dots on a circle. The amplitude here being a constant, then it looks like a circle. And those are my states, are the different phase shifts. If there are 8 dots, it's 8 PSK. If there's 16 dots, it's 16 PSK. QAM, bless you. It says AM in it, but the Q here stands for quadrature. And so it's also using this, I can think of the x-axis as cosine and the y-axis as sine. And so again, cosine and sine. So the Q is the giveaway to tell me, oh, you're using both sine and cosine. They differ by a phase shift. So I have to be careful about my phase shift. I'm phase sensitive. I need to know sine versus cosine. It's kind of like using Polaroid sunglasses, almost. The cosine axis, you can think of that as one polarization. The sine wave axis is another polarization. It's like I get 2 channels at the same time for free. I can have AM on cosine, but I can at the same time, I could have AM on sine. If they're both binary, then this is maybe a plus and minus 1 and a plus and minus 1 there. Right? That would be 4 QAM. But 4 dots in a square looks like 4 dots on a circle. So let's make it 4-level AM. If I want these to be, you know, same spacing, then plus and minus 1 and plus and minus 3. They're all separated by 2. All right, so 4-level signal on sine then gets me 4 dots in the other direction. All right, and 4 times 4 would be 16. This would be 16 QAM. That's 16 different states. Questions on that? Okay, but it's definitely sensitive to phase, and they are, when we use the word coherent, we mean phase sensitive. Okay, so Sienna has their big truck that comes by and they show all the brand new equipment, all the CenturyLink folks, and they go, coherent, coherent, that's the new latest greatest thing in optical. It's they're using these higher level modulation schemes that are sensitive to phase. Okay, so my receiver has to be more complicated. It's more than just, is there energy there or not, on or off, you know, binary AM, pulse or no pulse. But the payoff is the data rate, right? Everybody remember that, the 2 to the n stuff? I can get n bits every t seconds. Cool. Questions, comments? See, it's all too easy now. You just know this stuff like that.
Don't go that far now.
Well, then go back over it in a pond, right? How many people saw PON anywhere before they came to this class? Cool. Not many, right? But now it's an old friend.
But before I came to this class, it was purchase order number.
Oh, that's a good
It was.
Well, I can buy that. Or do I need a purchase order first? I need a purchase order before I can buy that, right? And a PON now stands for passive optical network, right? Passive means not active. What does that mean? That means no power, right? I don't have to plug it in. No electrical power. Right? And Why is that so popular? Because it's cheaper. Right? I don't have to supply electrical power. I don't have to put this thing in a building with a roof on the top and electrical cabling coming into the little shack or whatever it is, right? It can just be part of my class, my network, my optical network, right? An EDFA is an all optical amplifier. I don't have to plug it in. It's pumped by another color of light, right? That's the plug in an EDFA. Shine a different color of light in it. Bam. My glass fiber turns into an amplifier. Very nice. You don't have to plug it in. So if I'm in a passive optical network, can I have an EDFA? Sure. Yep. Good. Excellent. Absolutely. Right? It's all optical. No electrical power. Nice and cheap. Can I have a splitter with, there's some kind of electronic switching?
No.
No. Can I have an optical to optical regenerator? No. Good. I'm done. Everybody get that one?
What's wrong with the splitter?
Good. Nothing would be wrong with a splitter, but one that has electronic switching in it.
That's the key.
Something like a router or something that has signal processing in it. But yes, excellent point. This by itself would be okay.
Because I thought this, a lot of times they did that when network splitters.
Yes, right. And we talked about that coupling and how two fibers close together can form a splitter. That type of splitter would be all right.
Because of the passive.
Because it's passive, because I don't have to plug it in. There's no,
I actually chose the first one, and then I started searching for things about this, and then I read that nobody actually uses an amplifier in the pond, so I chose none of the above. I got this wrong.
it doesn't cost you much on the homework, but
I went back and forth with that one too.
did you?
So do they have problems because they don't use an amplifier, so they have to have a higher power source?
You wouldn't use an electrical
No,
amplifier.
well, yeah, I don't know.
That's the key. If you Wikipedia or whatever, it might miss that point, right? An electrical amplifier would never be used in a pond, but EDFAs are, as long as you only have the optical parts in that. Now, to use an EDFA, I've got a pump laser diode that gets electrical power somewhere, but that's not part of my network. Right, so say I have like maybe some kind of FDDI ring or something, and then I have a coupler here, and maybe I'm tapping off signals here too, right, add drops and whatever. This is my network. This is my passive optical network, right? But over here, if I've got an EDFA, then I can have some electronics out here. Current. I could have an add drop here in my passive optical network. Although decisions as to what to add is all electronic, and now I'm going to drop these signals from my PON, and this, you know, I can convert that to electronic, right? So this has a laser diode. And I could have photodetectors here that have electronics in them, maybe electrical amplifiers here, right? But they can't be inside my passive optical network. Like there was a PON picture in the fancy slides, and they made a nice. Oh, I thought I printed all that out. Anyway, you have it in your lecture notes. I was just trying to bring some proof that, yeah, see, we did all this. There it is. Yeah, this wouldn't be part of it. Oh, and here's the one I'm looking for. Obviously, I have a whole lot of electronics here in the central office and other places, right? But the part labeled PON here in orange, all this has to be just optical, no electronics. That's the point. Somebody else waffled around about amplifiers too. But yeah, if it's an electrical amplifier, then no, can't have it. But all optical amplifier could be part of a PON. Okay, good. Any others? If you think I'm wrong, send me an email. Different sources will sometimes say different things. I've seen Wikipedia actually is pretty good, but I've seen them do things like saying that in a single mode optical fiber, the light rate goes straight down the tube, which is not at all the case. But usually they're pretty good. Given a fixed geographic distribution between the central office and the individual customers, okay, so I'm not going to move any buildings around during my comparison here, right? Which fiber to the what's it architecture would use most fiber?
So I went fiber to the curb.
Okay, why did you go that way?
That just sounded familiar to me. Instead of home run.
Well, if you look in the lecture notes.
I didn't know which lecture notes to look in, actually, sorry.
So is LaToya here?
I think they were in 10.
Did you find those lectures? Okay, they were in like the last three that,
I'll see.
a lot of this was, but a lot of this was from other lectures too.
Lecture 7.
Yeah, I never went past 2, I think.
Oh,
You gotta read your, gotta look at the lectures. Or maybe.
Well, you know, it'd probably help me if you said these are covered with lectures, whatever, whatever.
Yeah, but see, I run into problems with my lawyer if I say,
Possibly could find this type of question.
homework 2 is
Through
covered
these
by
lectures.
lectures 7, 8, 9, and 10, then oops, if I mention dispersion, then it's, you know, so
Really?
that's part of your job as a student, is you
Yeah.
gotta sort through
Need to
it.
remember
That's one
that.
of the reasons for having homework, is to force everybody to go back over the lectures, look at the lecture notes, listen to the lecture audio, if you wanna call it that. So we had different architectures, and you know, I don't want you memorizing a bunch of stuff, a bunch of names or numbers. It doesn't seem like that's a good homework question or an exam question, really. So look at that lecture. There's, in those notes, there's tons of, and you had pre-lecture notes on this too. There's tons of useful information in there, but a lot of that stuff just doesn't yield itself to a good question for homework or an exam question. You know, how many homes passed in 2008? You can't remember that. That's not a good question, right? But what's passive, what's active in the industry, right? They differentiate between optical and electronic. That's a good question. Okay, so we have these different architectures. In home run, there's fiber all the way to every house. You've got a little box outside your house called a ONT and other names, but you have a little box outside your house that converts the optical signal to electronic. Right? But this is basically fiber all the way to your house, right? So, let's see, fiber to the curb is here. And then fiber to the curb, it's fiber all the way up to whatever they call this box. But this box then has copper. You can't really see it there, but you can see it in the lecture notes. That word says copper.
Gotcha.
DSL, all that jazz. So there's less fiber used because I got copper. It's fiber to the neighborhood. That's what fiber to the curb, one way of thinking of it.
Gotcha.
Cool. Anybody else? There was another choice there. What was that?
Active star.
Which?
Active star.
Oh, right. Active star. See, it's got the word active in it already. It makes me think that's going to have more electronics. And if I can find the picture, there it is. In active star, it's fiber out to, you might think of this one might run second place. It's fiber out to a electronic regenerator, and then it's fiber out to every house. But this is a shared fiber here, rather than having a fiber going to every single house, which is what home run tries to do.
Is that one like Roland?
I'm sorry?
Is that one similar to Roland? This active star?
Similar to which?
Roland?
Yes.
Okay.
Yeah. And in this one, you're going all the way out. You're saving fiber, right? You don't have to run fiber to every single house. You run fiber out to here, and then here you're running fiber from this box to every house. So there is, I'd say this one's using probably more than fiber to the curb. But home run is central office all the way to the house is fiber. Good. Any others? All right, so now the tricky bit. I gotta calm down and make sure I know which one I'm circling here. Home run. Now, that is the one who uses the most. All right, don't flip things. All right, I have two amplifiers. One has a gain of this and a noise figure of that.
Can't see us too.
Oh, thanks. Two amplifiers. One has a gain of that and a noise figure of that, and the other one has two other numbers. Which one leads to the smallest overall noise figure? So I give you real super short, I think there was 2 pages, and then I snuck in that marketing stuff on that noise figure. Stuff was basically 2 pages. So, again, if I had a noiseless amplifier, and I wrote a paper on that, showing that's impossible. somebody had some trick and he was gonna reduce this 3 dB noise figure by a factor of 2. In fact, that's 3 dB. That would mean a noiseless amplifier. I said, that can't be right. So I went over to Sprint KU Lightwave Lab, and they let me use all their fancy equipment. I did a big old experiment, took forever, just to prove that what's kind of obvious, you can't have a noiseless amplifier. But it was neat, and it was nice that they trusted me to not break all this very expensive equipment. And I went in there at night. Oh, the things I've gone through. Anyway, it was fun. But if you had a noiseless amplifier, then it would work just like a mathematical ideal amplifier. But an amplifier doesn't know a signal versus noise. It doesn't know which is which, right? It's not that smart. A regenerator tries to know the difference. It tries to remove noise and clean up the signal. So regen is more complicated, right? But an amplifier, its job is very simple. It just makes everything bigger, right? So in a sense, it might seem kind of silly now. Why do I need amplifiers? Right? It's just making my signal bigger, but it's also making my noise bigger. And then, as if that wasn't bad enough, it adds its own internal noise into it. So it actually makes the signal-to-noise ratio worse. But you need amplifiers because sometimes your signal, if you let your signal get too small, it falls into the noise floor, you can never get it out of there, right? If I can't hear that song, I can't hear it, right? I need an amplifier. I need to boost it up so I can hear it over all the background noise. So, but oddly enough, amplifier will degrade the noise figure because it has its own internal noise source. So how do you deal with that? Well, this is what it boils down to. You can write out the formula for as many boxes as you want, but you can always just take it one box followed by the next box. Take it in steps of 2. So I've never seen anybody use this formula beyond those first 2 terms. Okay, so that's why that one's in green. Don't really need it. So we did examples, and which one is F1 depends on which amplifier it goes through first. Okay, so I'll just use that. Now this one, that's a homework. I can use some numbers. Let's see. If this one, if I've got amp A in front of B, can you see? A followed by B. Then amplifier A is what I use for F1. F1 plus F2 minus 1 with G. So then F1 would be this one, right? Am I doing that right? Cool. So I have 10 plus the second one is 8 minus 1 divided by the gain of the first one, which is 7. Okay. So what's that? 11? How nice. If I have B in front, then what do I have? Then amplifier B is now F1. It has a 8 plus noise figure. The second one is now amplifier A, 7 minus 1 divided by a gain of the first one, which is B, which is a 3.
I think it's 10 minutes
Yeah,
away.
10 minutes.
Oh, thank you. 10 minus 1. Yeah, this one is now noise figure number 2. Thanks. And does that make it a strange answer?
Mhm.
Can you imagine how long it took me to find numbers that would do that?
You were being sneaky.
Oh, I was being cruel. Downright mean. 10 minus 1 is 9. 9 divided by 3 is 3. 3 plus 8 is 11. Yikes. Very rarely happens. I did that for a reason, though, right? And not just to be mean or sneaky. In this case, it makes no difference, right? Could I have seen that before plugging in the numbers? No, I don't think I could see that. So beware of rules of thumb, right? Where a lot of us are used to thinking, okay, a preamplifier, that's my low noise amplifier, I put that one in front. That's true if they both have the same gain, right? But here, it wasn't so clear. Okay? So when in doubt, work it out, all right? But if I made them the same gain, in most cases, at least, I don't even want to quote any general rule, but I'm pretty sure if I made them the same gain, then the low noise one up front always wins. Right? But typically in stereo equipment and any place where you're using a preamplifier, it's very low noise figure and it's also small gain is the one that goes up in front. When I really want to boost up my signal, I boost it up after I've amplified it with a preamp. Okay. Sounds like most people got that one. Numbers. Yeah. Sorry,
Trying to
is
trick it up, but we got
it- Good.
Nobody got number 9.
It probably was a little surprising. Well, we'll see what 9's up to. Okay, that's probably the shot noise or variance or something. But once you see it, you'll have it forever. Okay. All right. We talked about thermal noise and shot noise, and one has a Poisson PDF and the other has a Gaussian PDF. Which one does thermal noise have?
Yes.
Yep. Thermal noise is that Gaussian thing. I'm going to save time. You've all got your lecture notes, right? What's the spectrum of thermal noise? That's the part B here, right? Questions on that? All right, so where is that? Oh, run away on me. Too many stacks of paper. Need that. I'll take this from here. We'll find that later. What are we up to? Number 8. Sorry, I hate to waste time shuffling through papers, but sometimes they run and hide. Yeah, can do it from this one. Number 8, thermal noise has a spectrum that's what? It's not Gaussian. It's fairly flat, all right? That was the white noise. All right. This is out to like 10 to the 12 hertz at room temperature. It's flat. Over the bandwidth of most electronics, right? What's the dreaded number 9? Gee, it's so unpopular, it's gone and hid on me. There it is. Okay.
I don't blame you for hiding.
Okay. Here's the lecture notes on that. Poisson distribution has this interesting property that nobody else has, right? And this is very important in optical communications. It works this way. The average value of my signal is the same number as my variance. I want everybody to repeat that. In a Poisson PDF, the average is the same as the variance, or the same number. Now, the variance can be defined as the average, pointy brackets means average. This is right here. So, shot noise. So, that's French for fish. The fish distribution says the average value of the photon number is the same thing as the variance. Same number. Okay, so there's step one. I'll do step two in a different color. Step two here is what's the variance? Well, variance, you might define it to be the average. Let me write it cleaner, settle down. Take my random variable, subtract its average value, square it, make it more like power. Right? Current minus the average value of current, square it. And then take the average of that. We showed that can always be written this way. Oops, I started to do quantum theory. Don't put a hat. The variance of anything, remember I multiplied this out and then I took the average of it. Average value of 17 is 17 on a good day, right? The average value 2 times x, where x is a random variable, will be 2 times the average value of x, right? We factored all that out, simplified it down, and we got that this is equal to what's called the second moment, the average value of thingy squared minus the square of the average value of the thing. Okay, always true. Okay, so now I'm armed with my lecture notes. And so, let's see, the rest is just math. Expected value of I is 5. What's the expected value of I squared? So, expected value of I is 5. This is Poisson. So that's also the variance. Same number. Okay. And then I can always write the variance as the average of the square minus the square of the average. So that is average of thing squared minus, I have that right here. Average value of I is 5. 5 squared. In other words, just rearranging some terms here, this will then be equal to 5 plus, what's 5 squared? 25. What's 25 and 5?
30.
that on my list? Good. Okay. You'll see why later, why I'm making a point about that, but in the textbooks and things, they get a little sloppy. Even the best textbook that I've seen on optical
Negative times
communications
negative, negative plus.
by Agarwal, he says, I'll come back to this point. But it's also to force you to look at the lecture notes, learn a little bit about Poisson. Poisson has this weird property that the mean and the variance are the same number. And then variance can always be calculated this way. Questions, comments?
Yeah, you lost me where you jumped from equal I squared minus 5 squared,
Okay,
and you jumped down to, and you got
yeah,
5 plus 25.
yeah, all right. I've got, if you follow through, there's 5 equals. So I've got 5 equals this minus that, right? So then I just took this and moved it to the other side. It's just algebra, right?
You know, just not getting along.
So let me do it as an aside. I've got 5 equals, yeah, that's where I usually panic. That's where I say, give it to Mathematica.
So where did you get that? 5 equals the I squared minus, 'cause
Okay.
maybe that's where I'm getting.
Where did that come from? Step by step. I was given this,
Uh-huh.
and then this,
What is that symbol? I was trying to, I looked at it
This
on the
is-
lecture and I don't understand what that's the variant, it means.
yeah,
variance?
that's a symbol for variance. It's a sigma squared.
Okay.
And then you put a subscript for the thing you're talking about. If this was X, I'd have an X there. If it's N, I have an N there. This is I, so I put an I there. But yeah, that's just common, that's standard notation. I don't know where it came from, we're stuck with it. Sigma squared is a symbol for variance, shorthand for variance. Right there, if you like. So this was given, right? And then this is from the fact that it's Poisson. Those are the same number. Right? Then the next part is because I can always write variance this way. Okay. Then the part after that is algebra, the dreaded algebra.
I think they don't realize you're solving for I.
I'm solving for expected
I
value.
equals I
I
squared minus
squared.
5 squared.
Expected value of I squared is what I'm solving for. So there's also English language here. You're getting exposed to expected value, there's the average value, right? Which I can write this way, average of I squared. It's got a lot of learning going on in one question. But getting back to your question, was a matter of algebra, right? I had this, so I add 25 to both sides. Getting back to your question, I had this, and so I add 25 to both sides, and that tells me that. That was the algebra.
Because you dropped the negative is why he moved it to the other side.
Yeah.
Or if you say -5 times -5. you're
Well, I
No,
was just
no.
saying to
Negative.
Steve, because he didn't understand why,
Ne-
how he
ne-
got that.
Put your parentheses in the,
If you keep a parentheses, you'd still stay negative.
in the right place. You say
But if you got
negative
-5 times
negative.
-5.
of 5 times 5. -5 parentheses times a -5
Would be.
would be something else,
Awesome.
right? Yeah. It's got a lot going on. How do you like 10? 10 a little easier? But 10's worth remembering, right? Thermal noise goes like that, right? Shot noise goes like that. Or this is frequency. So, like we said, this thing drops off at room temperature, that's about 10 to the 12. At 1550 nanometers, that's like 10 to the 14, 10 to the 15. Numbers like that. Then I'm out here. And shot noise is the dominant source of noise at optical frequencies. It doesn't mean thermal noise isn't important. On the electronic side of things, I could have a lot of thermal noise. But in the electromagnetic field itself, there won't be. Well, I don't want to introduce any new material before the exam. So,
Thank you.
whatever time it is, we're done. Good luck on the exam. Just keep your cool. You got plenty of time. You'll be
So is there
fine.
up to possible lectures that might be covered on the exam, sir?
Yeah, all the lectures we've had are fair game.
That are on the site?
Yeah.
Homework
That's right.
3, you said you were gonna discuss what date are you
Oh,
planning for homework
yeah.
3?
What are your feelings about homework 3? You want,
Tuesday.
Tuesday
just-
before the 8th. 8th is the,
okay. So,
Sooner the better.
I mean, I could put it out there tomorrow,
Yes, that'd be good.
but I don't want anybody thinking it's part of the exam.
We would say
So-
homework 3, right?
Yeah. I think why don't I put it out
Monday.
after the exam is due? I can put it out Sunday if you like.
It's gonna be on stuff we haven't covered yet anyway, isn't it?
Yeah, there'll be lectures that I could record those and have them ready to upload from. It'll be all right, trust me. We're not in a crunch.